All right, so as we continue here in section 3.3, we're going to get to the heart of the section, which is the derivatives of the inverse trig functions. But first we need to remember just a little bit about where these inverse trig functions came from. So we're going to kind of review here. There's a little summary. I'm just going to take a look at maybe one function and just kind of jog your memory as to what happened when you talked about these functions in trig. So suppose that we started with our tangent function. So suppose we had f of x equals tangent of x. You're probably a little more familiar. You probably remember your sine and cosine. Typically students remember those a little better than maybe than the tangent. But your graph of tangent, if you recall, you had vertical asymptotes. This is the fundamental period, at negative pi over 2 and at pi over 2. But of course those continued kind of at all the half pi's. So there's another vertical asymptote at 3 pi over 2, and there's another vertical asymptote at negative 3 pi over 2, and those of course continue. And then our basic graph here of this function is we had curves that kind of approach, it almost looks a little bit like the x cubed graph, but approaching the vertical asymptotes. Of course it's not, but just if I had to, describe it, I might say it looks a little bit similar there. And then it continues, right? All of your trig functions, are periodic, and so they all have this repetition. They have different periods. The period of sine and cosine, for example, is 2 pi. The period, after which it repeats, kind of the width of one of these is pi, right? It goes from negative pi over 2 to pi over 2, so one period is pi, and then it repeats after that. So if you recall, in order for a function to have an inverse function, it has to be 1-to-1. So if we were to think about this entire function, we would say it's not 1-to-1. So initially we would say there can be no inverse function on the entire domain. But then we very quickly say, well, let's just restrict it to a region that is 1-to-1. Okay, so then what we say is, okay, and we say, like for tangents, we use the fundamental period here from negative pi over 2 to pi over 2. Now, could they have used the one from pi over 2 to 3 pi over 2? Sure. But this is sort of the conventional domain restriction in order to make it 1-to-1. So what we do is we restrict the domain to, in this case, just negative pi over 2 to pi over 2. So it is 1-to-1, and therefore will have an inverse function on this portion, right? So that's what you do, and you talk about that in more detail in trig. So when you go back up to the top, you can see to this table the negative pi over 2 to pi over 2. So there's your restricted domain. And then, of course, you can look at the range. It goes from negative infinity to infinity. All right, so then if you remember, so what happens just with inverse functions in general is a switching of all of the x's and the y's. That's really what defines, it's this notion of doing the opposite. And another way to think about that is the inputs and the outputs all switch. So if I'm going to think about then taking a look at arctan, so then if I'm going to graph arctan of x, or if you prefer, I'll use both, we could call that tan inverse of x. So what we're going to do is just kind of think about, if you just, literally if you took all the ordered pairs on tangents and you just switch their x's and y's, that's how you get the graph of tan inverse or arctan. Another feature that we kind of get out of that is that the function and its inverse function, their graphs are symmetrical, or they're mirrors of each other, over the line y equals x, the line that bisects the first and third quadrant. So however you think about it, what ends up happening is that where you used to have vertical asymptotes at x equals pi over 2 and negative pi over 2, you're now going to have horizontal asymptotes at y equals pi over 2 and at negative pi over 2. And so these are now going to be our vertical asymptotes are now our horizontal asymptotes. And then basically the graph, just kind of ends up looking, you could verify this on your calculator, but it, ends up looking something, not perfect here, something like this, roughly. That is our graph. So this is sort of what happened. And now if you kind of look at, well, what did that mean? So notice if you go back up to the top here and you look at these relationships between some of these things. So what happens is, all of the domains are going to, of the original function, so all of those domains are going to become the ranges on the inverse function. So the domains and ranges switch, and vice versa, right? So the ranges of the original functions are going to be the domains of the inverse functions. And so I just want you to kind of remember some of these basic ideas here. Now, the other thing too is just how we evaluate these inverse functions, right? So now you're trying to think of an angle whose tangent, for example, is 1. So if I was to think about, so another important thing to just kind of remember here is if I was to say then, well, what is, tan inverse of 1? You're thinking about, for what theta, let's say, is tangent of theta equal to 1. And you'd be like, oh, I gave us 1 on the unit circle. That's at pi over 4, for example. So if I said tan inverse of 1, at 1, you would be at pi over 4. So, also just remember some of those ideas as well, just how to kind of evaluate some of those. One last quick comment before we go on to coming up with the derivatives. The last two, secant and cosecant, those, if you were to look back in your trig books and other calc books, those are a little bit different. Remember when I just said with tangent, I'm like, could we have restricted it from pi over 2 to 3 pi over 2? Sure. We just need an interval that's 1 to 1. It doesn't matter what region we use. So this book took the liberty of taking a slightly less common, maybe, approach to those. But it does make the derivatives that we have for those two a little bit nicer to look at. So just a comment in case like you just were to Google those two or to look into a different book. They are a little bit different than the usual. All right, so what I want us to do now is to take a look at, so the derivatives are all written here for you. I want us to prove at least maybe just one of these. So let's take a look at, how about cosine inverse? So let's look at just a quick sketch of the proof here. So suppose we have, there we go. Okay, suppose we have, let's let y equal cosine inverse or arc cosine, whatever you prefer, of x. I'm trying to come up with this derivative, and in theory, I don't know what it is. So what could we do? Well, how about we think about just simply rewriting this in terms of cosine. So if you were to take the cosine of both sides, so if you were to take cosine of both sides, you would have that cosine of y is equal to cosine of cosine inverse of x. So x is equal to cosine of y. All right, now what we want to do is now we want to apply our differential operator. So we are going to take the derivative with respect to x of both sides. Now on the right-hand side, derivative with respect to x of x is just 1. Derivative with respect to x of cosine of y, well, derivative of cosine is the opposite of sine of y. but we just are taking a derivative of y, which if you look back, y is equal to cosine inverse of x. We're treating y like a function of x. So we have our little implicit differentiation step here to consider. We multiply by a factor of dy dx. Okay, so now we are trying to solve for dy dx, right? That's the whole idea. So if I divide both sides by my minus sine y, it feels like I've just isolated for dy dx and have, but that certainly doesn't look like the form that I've written up above. I don't have it written in terms of y, I have it in terms of x. So let's think about trying to get this back in terms of x. And what we want to think about here is we want to go back up to, let's say, this step right here. And what we want to think about is if x is equal to cosine of y, let's even say cosine of, oops, I meant to put that over 1 on the other side. So let's say cosine of y is equal to x over 1. Now, if you think about right triangle trig here, so if I was to say, let's think about just putting y as an angle in a right triangle, then cosine of y becomes the ratio of adjacent over hypotenuse, which is why I made it a ratio over 1 there. So the adjacent side would be right here, the x, and then the hypotenuse is 1. And so in order to find the missing leg here, we would say, all right, well, x squared plus, I'm trying to find this leg right here, let's call it question mark, squared, is equal to 1 squared, or just 1. And so I'm trying to solve just a little Pythagorean theorem here, so 1 minus x squared, and then I take my square roots, and of course that's going to tell me that this missing leg is going to be 1 minus x squared. Okay, so if I kind of just go off to the side, I get that this leg is going to be the square roots of 1 minus x squared. All right, so now if I think about then going back here to my dy dx equaling minus 1 over sine of y, well, if we think about sine as a trig ratio, sine is equal to opposite over hypotenuse. And so we would now have our negative 1 over, I'll take that reciprocal in just a second, the opposite side of y, for sine of y, is going to be 1 minus x squared divided by the hypotenuse is 1. And so actually, in the end, here's what I now have. My dy dx here, dy dx, is equal to negative 1 over square roots of 1 minus x squared. And so that is the form of the derivative that you see up above. So here are all of my derivatives of my inverse trig functions. The only other thing I'll say is we also need to be able to think of these in terms of in conjunction with their chain rules. So remember, if I was going to write this out with a chain rule, it would look like the derivative with respect to x of sine inverse. Now, if what's inside of that sine inverse function, if that is some f of x, so something more than just a plain old x, that is when we have to think about applying chain rule. So derivative of sine inverse of f of x is going to be 1 over the square root of 1 minus, and your f of x gets left alone, so this is the derivative of the outside with the inside left alone, and then by chain rule times the derivative of the inside. And you could just slide that into the numerator if you wanted to as well. And so this is how all of these would look. Start to make some early observations here that obviously, let's write out a couple more along the way here. Let's say I looked at the derivative with respect to x then of tan inverse of, again, suppose that my inside was an f of x function, so more than just a plain old x, then that derivative is 1 over 1 plus the f of x, the inside function left alone, so that's the derivative of the outside with the inside left alone, so that's squared, and then times the derivative of the inside, so times the f prime of x. And let's continue here. We'll write out dot, 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 and then we'll maybe go down to the very last one here. So let's say we had the derivative with respect to x of cosecant inverse of f of x. And so that one, again, its derivative of the outside looks like negative 1 over, and then there is an x on the outside, so that would now be an f of x on the outside of that square root function. And then times the square root of, and then there's an x, so that inside left alone, so the f of x. And so it's that f of x quantity squared minus 1, that's all under the radical there, and then times the derivative of the inside, so times the f prime. All right, so those are a few. They all kind of look the same then at some point there. So taking a look back, notice that the cofunctions are just the negative, so the derivative of our cosine or cosine inverse is just the opposite of that of sine inverse, so just an observation. So we'll come back next time, we'll actually look at some examples of these.